as can be seen in this clip, has been named after the observation that breakfast cereals floating in milk will often clump together in the middle of the bowl or stick to the walls of the bowl. This clustering arises due to the distortion that occurs at the liquid-fluid interface by the presence of the wool known as the meniscus effect. Because the cereal is buoyant, there is a net upward force due to gravity, which acts on the cereal. As the Cheerio is constrained to lie at the interface, it cannot rise vertically and therefore moves up along the meniscus. This phenomenon is also present with the attraction of objects that have a higher density than water. The reason these heavy particles can float at all is due to the presence of surface tension, which prevents the interface from deforming downward in a manner that would cause these heavy particles to sink. The deformation that occurs at the interface for these dense objects is opposite to that found on a buoyant object, as the surface tension must act to counterbalance the weight of the particle. Objects with similar deformation at the interface are attracted to each other, as can be seen with these paper clips. Although two objects of similar weight characteristics are mutually attracted to each other, what if now we were to place a buoyant object, such as a Cheerio, and an object that relies on the surface tension, such as the paperclip, on the surface of a liquid? Based on the previous argument, we would expect to see the Cheerio move up along the interface that has been distorted by the presence of the paperclip. However, this does not occur. Because the paperclip is buoyant, the interface has the opposite curvature of that of the cereal and will cause the Cheerio to move away from the paperclip, and so the two objects appear to repel each other. Another simple experiment that demonstrates this repulsion can be achieved by using a drawing pin with a plastic cap. If we remove the cap from the drawing pin and place the pin and the cap on the surface of the liquid, the two objects will move apart. This experiment challenges the assumption that attraction and repulsion of particles at the interface depends solely on the wetting properties, and rather indicates that the change in the sign of the curvature can be brought about without changing the surface properties of the cap, and rather it occurs due to the change in the effective density of the particle.
Two plus two is 4, minus 1, that's 3, quick maths. Everyday man's on the block.